Hi, are you guys there?
Good evening, sir.
Hi.
Hello, sir. Good evening, sir.
Hi, Jhalak. Let me. Hi, Anusha. I have to. Can you just see my?
Sir, the screen is frozen.
Yeah.
No, sir.
So you have to share the whole screen, sir.
Okay.
Not only this tab.
So I have to share the whole screen. What does that mean?
Now it is visible, sir.
Yeah.
Yes, sir.
Okay. Okay, this is gonna be a bit tricky, I guess. Okay, is that better? Yeah, okay. Okay, let's wait for a few minutes. So are you guys in Delhi or outside?
No, sir. We are at our hometown.
Hometown. So what are you guys expecting? You're expecting to come back, or I mean, I don't think it's going to be feasible, at least in the next few months. So we'll have to think of ways to set an exam and things like that. Do you guys have any suggestions?
Sir, I think take-home exam is the only option.
Take home. Yeah. No, we are thinking about it. There's no other. There is no. Alternative. Jhalak, I think you even have to give the midterm, right?
Yes, sir.
Yeah. So how? I mean, we have to worry about all these things.
Sir, have you checked the
Yes, sir.
midterms?
Yeah, I have actually. I had done most of it, but not completed it. So I will go back and complete it.
Okay, sir.
So
So you can, Tridip sir told me that I can score at most 60% in the midterm.
Achha.
So you can give me assignment. I can complete that instead of midterm. I'm okay with that, or I'm okay with the exam as well. Whatever seems feasible to you, sir.
The problem is that the exam doesn't make a lot of sense, right? I mean, I don't know. I mean, I don't know what I can give you. I can set you something and ask you to upload it, scan it, and
Yes, sir.
you can do that, right? You can scan it and
Yes, sir. Yes, sir. I can do that, sir.
okay. Remind me. I mean, it isn't that I have to do it at a particular time or anything.
So sorry, I did not get you. What?
So it's not that it has to be done at this particular time or that particular time or anything like that, right? I mean, it can be at a, I can give it to you, next week or 2 weeks
Yes.
from now or whatever.
Yes, sir. Yes, sir. Because in micro also, I was not able to give the class test. So Sir Prabal sir gave me the assignment, and he gave me the window of, I guess, 1.5 weeks, and then I scanned the assignment and submitted him.
I see. Okay.
Yes, sir.
And you've done it already for Prabal.
Yes, sir.
Okay. So are all your classes going on, or some of them are not going on, or what's the?
Sir, I guess environment class is not taking place. Otherwise, all subjects, all classes are going on, sir. In
Yeah,
macroeconomics,
environment is not happening. Yeah.
What?
Yeah, environment is not happening right now.
Sure.
and in macro, our syllabus is complete, sir. So classes are over in
All-
macro and development economics.
And also, Devashish is also over, right?
Yes, sir.
That second year.
Yes, sir.
Achha. Okay.
Sir, what's the coronavirus update in your area?
In my area. You mean in Delhi? Are you in Delhi? Do you mean in my neighborhood in Delhi? And
Sir, neighborhood.
there are places which have been shut down. I mean, there was some nursing home nearby which apparently had a patient. But you see, they are not testing, so it's useless. Just going and shutting this thing down. It causes enormous. Today morning the police came and there are some vegetable vendors. Now the RW has complained that these guys will spread the disease from their neighborhood, so you should stop them. But that makes very little sense. I mean, if you have to go to the vegetable store to buy, you are actually at bigger risk because there are far more people there. You have to test these guys and have the results in a few hours to say, yeah, they're fine. Anyway, it's a mess. I don't know what's going to happen the future looks very unsettled. I frankly don't think that there will be regular classes. Hang on, I have to admit somebody, right? There are many people. Have all these people already joined automatically? Prajwal.
Yes, sir.
So you guys are all there. I didn't have to let you in or anything like that.
No, sir. No, sir. It was automatic.
Okay, good. Okay. Okay.
Good evening, sir.
Hi, Nandi. So far, everybody is well. Nobody knows anybody who has the thing, or
So far, so good.
so good. Okay, I'll wait for another 5 minutes or so. Any questions, perhaps?
So for the last lecture, can I ask one thing?
Yeah.
This is regarding the permutations approach to your, what is it called, the substitutes part.
Yeah. I am going to say something more about that. I'm going to give a full proof of that.
Proof that symmetry holds.
Yeah.
So why do you need a full proof? I have one thing to ask.
Yeah.
So fix a permutation P and players I and J.
Yeah.
Such that they are substitutes.
Yeah.
So within that permutation, without loss of generality, let us assume that I precedes J.
Yeah.
Now look at all those players who precede I. Let's call them the set A.
Yeah.
And let us look at all those players who are strictly between I and J. Let's call that set B.
Yeah.
Then A union B doesn't contain I or J.
Yeah.
And neither does A. So clearly.
Yeah.
So therefore, V of A union I is V of A union J.
Yeah. So this is exactly what I was going to do. So that's exactly.
And similarly for A union B, right?
Yeah.
And therefore for the flip permutation with I and J flip, the same thing.
Yeah. So that's I was going to do it for the counting coalitions thing, because I'm also actually going to be using the coalitions. It's kind of today we will be looking at a lot of coalitions, weights and coalitions. So I was going to begin by doing that. It's the same argument as the permutation.
Okay.
So just give me 1 second. Okay, shall we? Okay, let's wait 1 more minute.
So why are you not visible?
Uh, I don't know. Is the screen visible?
The slides.
Slides
Yeah,
and you
slides. So that's fine.
Have you switched off the video by any chance?
No, the video is also
visible to us.
Video's on, but I mean, if I share the screen, then I don't think you can see me.
No,
Last
sir.
time
We
we
can
could.
see both.
We can see both.
We can see both, sir.
How can you see him? I cannot see him.
There is an option on the top panel, view options.
View option. Oh, I see. Okay. And what to do with that?
Side by side mode.
Side by side. But I can see you, Manoj, not him.
You will have to pin sir's video.
Yeah, go to gallery view and there pin sir video.
Okay, so shall we begin?
Yes, sir.
Yes, sir.
Yeah. Okay. So I just wanted to briefly discuss that point about symmetry. Okay. To show that if two players are substitutes, then their Shapley values are the same. So let me give you an argument according to coalitions, and I'm doing this deliberately because we will be seeing a lot of arguments like this today instead of permutations. It's as Siddharth was saying earlier, there is an equivalent argument in permutations, virtually the same thing. Okay, so suppose I and J are substitutes in V, and let us consider the marginal contributions of I and J to various coalitions. So as you know, the Shapley value is the weighted average of such contributions across coalitions, and these coalitions which differ only in size. Okay, so we have two types of coalitions. So one coalition S is so for one coalition S, these are things which don't contain either I or J. So these are subsets of N minus Ij. And here you observe that just by observation that V of S union I minus V of S is equal to V of S union J minus V of S, because V of S union I is equal to V of S union J, since since S does not contain either I and J. Okay, now you have another case to consider, So we are looking at it from the point of view of player I, okay? So let S be a coalition which contains J but not I, okay? Now let S prime be the coalition obtained by removing J from S and adding I, okay? You just take J out from S and add I, and let's call that S prime. So obviously S and S prime are of the same size, okay? Now let T be the set obtained by removing J from S. In other words, T contains neither I nor J. Okay, so notice that T union Ij is equal to S union I, because S contains J, now you add I, and it is equal to S prime union J, because S prime contain I but not J, you add J, now you get these things, right? Also, S is equal to T union J, and S prime is equal to T union I, right? So these are just, now let's just look at V of S union I minus V of S, okay? And V of S union I, as we know, is just from the earlier thing, is T union Ij, and V of S is T union J. Okay, that's one. Right, now we keep the first term the same, T union Ij minus V of T union I. Now why is it that V of T union J equal to V of T union I? Because I and J are substitutes and T contains neither I nor J. Okay, is that clear? So V of T union I is equal to V of T union J because T contains neither I nor J, right? So we started with some coalition for I, some S, which contained J. So what you did was you removed J and you added I, and you looked at the set of all other elements and called it T. Okay, so V of S union I is T union Ij, and V of S is T union J. Okay, so this, by virtue of the fact that I and J are substitutes, we know that V of T union J is equal to V of T union I. So that's equal to V of S prime union J minus V of S prime. So the point here is that I and J make the same marginal contributions to coalitions containing I. So this is the first, summarizing, this is the first point that I made. Players I and J make the same marginal contributions to coalitions not containing I or J. That was the first part, that's immediate. And then suppose we look at I's contribution to a coalition containing J. Then there exists another coalition where J makes the same contribution to S prime where I is present, right? That part is not important, right? So for every coalition S containing J, there exists a coalition S prime containing I, such that I makes the same marginal contribution to S as J does to S prime, and the size of these S and S prime are the same. Okay. Moreover, when you are computing the weighted contribution of player I, you are going to look at set S, but not set S prime, because in S prime I is present. Likewise, when you are looking at the contribution of J, you will look at S prime, but not S. So basically, what we have is this 1-to-1 map for, every time I have a coalition S which contains J, right? I have another coalition which contains I, which is of the same size, where I makes the same contribution to this coalition as J makes to the other one. Okay, and the Shapley value is simply the weighted contribution of players to coalitions, and this is important, that the weights depend only on the size of the coalition. It doesn't depend on who is in what coalition. Okay, and this immediately implies that if you just write it all out, that Shapley value of I in B is the Shapley value of J in B. Okay, so I've said I's contribution to S prime is not considered since I is in S, and J's contribution to S is not considered since J is since I is in S prime and J is in S. So let me even give you an example. Okay, so suppose n is equal to 1, 2, 3, and 1 and 2 are substitutes. So it means that v1 is equal to v2. Why? Because in this case, you are adding 1 to to the null set and 2 to the null set or the empty set, right? Which therefore v1 is equal to v2. Also, v13 is equal to v23 because the left hand side is what happens when you add I to the set 3, and the right hand side is when you add 2 to the set 3. So the Shapley value of I is the weighted contribution of player I to the coalition's null, 2 to the coalition 2 to 3 and to 2, 3 with weights 1/3, 1/6, 1/6 and 1/3. The important thing is that the weights depend only on the size. So singletons get 1/6, null gets 0, null gets 1/3, and 2, 3 gets 1/3. And likewise, the Shapley H2V is the weighted contribution of players 2 to the coalition's null, 1, 3, and 1, 3. Again with the same weights, right? For depending on null, singleton, or 2 elements. Now let us see the contribution. Observe that the contribution of 1 and 2 to null and 3 are the same, because these are the sets which don't contain either 1 or 2. Okay, and we know that the marginal contribution is the same. Now look at the contribution of 1 to the coalition 2. That is exactly, by our previous argument, the equal to the contribution of 2 to the coalition 1. That's exactly the same. And these contributions are weighted by the same number, which is 1/6. Likewise, if you look at 1, 3 and 2, 3, okay, what's 2 appears in 2, 3 and 1 appears in 1, 3. But what you can do is that 1's contribution to 2, 3 is exactly equal to 2's contribution to 1, 3, right? Because of what I did in the second bullet point, they're exactly the same. And moreover, the weights are the same. So when you compute this average, then over certain coalitions, the contributions are the same. These are things which don't contain either 1 or 2. For the remainder, for the other coalitions, every time you have a coalition which contains 2, there is another coalition which contains 1 but not 2, and the one's contribution to 2 is exactly equal to 2's contribution to the to the other coalition, to the other coalition that I have constructed, and the weights are exactly the same because they depend only on the size. Therefore, SH1 V is equal to SH2V. Is that clear? Is there any doubt, confusion? Right. So you just have to keep a careful track of the values that you're adding to various coalitions. You could have done this argument for permutations as well. What you're adding here, you're adding somewhere else, etc. You have to make those kinds of arguments. Okay. Okay, so what I'm going to do now is I am going to we're going to talk about I'm going to talk about why is this? How do I get the other? So I have to stop share. I want to put on another slide. Should I click stop share?
You can do that, sir.
Huh?
You can do that. Stop share and then reshare.
When you share again, you'll get the option of which screen to share. So you can share the other one now.
Okay, so I stop share.
Yes, sir.
Okay. Oh my God. Now what happened? Share screen. Okay. Why do I get this screen instead of my my computer screen? Okay. Let me try.
So it's
Uh,
visible.
sorry, what happened to it? Is the new screen visible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So today, what we're going to do essentially is to look at a new class of games, or not a new class of games, a special class of games called voting games. And the idea here is to try and measure the power of individuals in voting games. Okay, how influential is an individual, in a voting game? Okay, so so a voting game is sometimes called a simple game, and you may have actually come across this in a problem set. So this is again a game in coalitional form, which has some very simple features. One is that the value of any coalition is either 0 or 1. Okay. In particular, the value of the empty set is 0. The value of the grand coalition is 1. And moreover, the structure is monotone. So if it is the case that VT if VS is 1, then any superset of S must also be 1. Okay, so what you should, if VS is 1, then we say that the coalition is winning. Okay, and if it is not 1, we say it's losing. And the monotonicity property is that all supersets of winning coalitions are also winning. Okay, so if S is a subset of T, subset of N, then V of S is less than or equal to V of T. So if something is winning, then all supersets of it are also winning. Okay, so how should you interpret this? I mean, the interpretation is that if the coalition S is winning, then it can adopt an issue that everybody agrees on. So there is an issue on which voters can vote yes or no. If F is winning, it can adopt the issue if all members in S vote Y. So it's like saying that you need 2/3 majority to pass a bill, and then any coalition of which has at least 2/3 of the members is winning, because if they agree, they can pass the bill. Okay, so the important thing here is that the grand coalition is winning, and the empty set, the null set, is losing, and a superset of a winning coalition is winning. And you can think of winning, you can think of a voting game as identical to just a collection of winning coalitions, right? So these are the winning coalitions, and these coalitions are have the property of monotonicity. So if something is winning, then a superset is also winning. Okay. Okay, by God, did I start?
Sir, is the
Hang on. Let me see if
it is recording, sir?
It is recording.
It is recording. Okay, good. Yeah, tell me.
Sir, in the last class, we did the example of basis game. So is basis game a voting game?
Yeah, because those are all zeros and ones. Yeah, so it is. Right, and by the way, and the fact it has this monotonicity property.
So can you explain this background story part again, that if S is winning, it can adopt the issue if all members.
Yeah. So let me give you a few examples, and then
Why even
give you
when
the examples,
everyone
and then tell me if it makes
what-
sense. Okay. So here is an example is a dictatorial game. So basically what it's saying is that if you want something to pass, then
Sure.
this guy has to agree to it. So in other words, we just say that a game is that this is a simple game where a coalition S is winning if and only if this dictator is a part of that coalition. Right? So if there are n players, there are 2 to the power n different coalitions, including the null coalition. And for every coalition, I give 0 or 1. and I give 1 only if this dictator is present there. Okay, so what's a majority game? We say that S is winning if the cardinality of S is greater than equal to n over 2. And a weighted majority game, there exists weights for every player, and there is a quota such that for any for any coalition S, something is winning if the sum of the weights for the members of that coalition exceed Q. Then it is winning. In other words, V of S is equal to 1. Okay, and the condition above just makes sure that V of N is 1. Okay, so for instance, in many organizations such as the United Nations Security Council, we'll just be discussing this actually. The European Union, the ICC, there are many classes of members. For instance, there are permanent representatives, there are non-permanent representatives. In the ICC, there are full members, associate members. Full members are members, for instance, of test-playing countries. Associate members are non-test-playing countries. So imagine that these are all there, and whenever, for instance, you have to make a decision where to hold, the next World Cup, what you will do is that you will get votes from all the members, the permanent members, the associate members, the full members, associate members. And depending on, if the number of people who say yes, if that is a winning coalition, then you will adopt that. Now, the question is, what extra features does it capture? I mean, the fact is that we could have, look at your class. I mean, I could say that, I need, that this is, in order for, I want to change the timings of this lecture, but I will change it only if 2/3 of the first years and 1/2 of the second years and all the PhD students agree to it, or something like that, right? So I can write that down, then that becomes a voting game, right? So the idea is that if, I have to decide on an issue. Think of it that way. I have to decide on an issue, where to hold the next World Cup, whether to have, take some decision. And then I ask everybody to vote, and then I count the votes of the people who, votes of the people who say yes. And if the set of people who say yes is a winning coalition, then indeed then the resolution is passed. Now, is that clear? Is it clear? Or do you need more clarification?
So one question.
Yeah.
Would it be fair to say that given a particular voting game,
yeah,
there exist certain minimal coalitions which are the winning ones?
Yes.
I mean, no two being contained in each other.
So there will be some minimal coalition, right? Because they are winning coalition. So minimal winning coalition is one in which the coalition is winning, but no proper subset of that is winning.
And therefore, no two minimal coalitions will contain each other, right?
No two minimal coalitions can contain each other. True. Yeah.
Excuse me, sir.
Yeah.
So, sir, you mean that if S is a coalition which is winning, then if all the players in that coalition vote say yes, then that issue is passed, right?
Yeah, it's the power. Think of it as the power of the coalition. That coalition has the power. It has the power to make a decision, to say yes. Right? So that's the way. It's the power of the coalition. Does that coalition have power or not? That's the idea.
Okay, all right, sir.
Yeah,
Answer the cardinality of that minimal set can be greater than equal to 1.
Yes.
Like in the majority game.
I could have an even more extreme case. Suppose I have the following game. That I have the following game. suppose I say that you know, V of n is 1 and V of all smaller coalitions is 0. I can do that. Okay. So so only the grand coalition. So what is the minimal winning coalition? It consists of all players. In the
So the set of minimal winning coalitions is greater than equal to 1.
The set of winning
Minimal,
coalition. Yeah, a minimal winning coalition.
yes,
Yeah,
sir.
that will be the case.
Like in the majority game, we can have more than.
I just gave you one example where it's exactly 1. There's only one winning coalition.
Okay, sir.
Yeah,
So
everybody has
it's
to
a
agree.
dictatorship, right?
Sorry?
So it's a dictatorship.
Dictatorship, a minimal winning coalition consists of just the dictator.
So that's again 1, right?
That's again 1.
Sir, and the minimal coalitions may intersect with each other, right? There may
Yeah. So, for instance, majority game. I mean, in majority games, for instance, if there are 3 players, then all minimal winning coalitions are of size 2.
Yeah.
And they will intersect, right? 1, 2. If there are 3 players, 1, 2, 1, 3, 2, 3, etc.
Yeah.
And so, for instance, different members have different rights. For instance, permanent members in the Security Council have veto powers that all of them have to agree, right? All these situations have to, can be represented by a voting game. And what is the central question that we are interested in? The central question that we are interested in is how do we assign, not how do we assign, what is the voting power of every player? That's what we're interested in. How do we define that? Okay? Because different coalitions are winning, etc. So there are many ways to do this, and I'll discuss many notions today, right? There'll be no theorems today, actually, but just many definitions or many proposals. So here is, I'm interested in power indices and measures. The difference will be clear. So script G is a class of voting games. And what is a power index is a map from G to 0, 1 such that the phi I of V over I is equal to 1, for all NV in G. So in other words, this is just like the value operator of a game, right? So 1 is like the total power that you can have. 1 means phi IV is the power that player I has, and the sum of the powers of players is equal to 1, which you can just interpret as the way that the value of the worth of the grand coalition is split amongst the various players. Okay, so the grand coalition has total power and has power. So how do we split that amongst the individual players? Now notice that simple games, I should have emphasized this earlier, a simple game or a voting game is a restricted class of games, right? So if we try to do axiomatizations and so on and so forth, we might not be able to pull off the Shapley trick, because some of the axioms may not apply, right? In fact, let me say that right now. So what will not apply? For instance, additivity cannot apply, because if you have 2 games, V and W, then V plus W is not going to be a voting game. Why? Because V of n and W of n will both be 1, and V of n plus W of n will then be 2, which makes it a non-voting game. Okay, so a power index is just, you think of it as a way to split the value of the grand coalition, and phi IV is phi IV is interpreted as the power of player I and V. For instance, here is a typo. It would be natural to require phi I v equal to 1 if V is the dictatorial game and I is the dictator. So in the majority game, for instance, you might want to say 1 over n, because players are symmetric. Also, the game in which you have only the grand coalition is winning, you might want to say that all players have power equal to 1 over n. Now, instead of a power index, a power measure is just a map for each player. So the sum does not have to add up to 1. Okay, the sum of the powers of individual players do not have to add up to 1. You can convert it into an index by just normalizing, but I'm defining a power measure separately from an index for reasons that will be clear shortly. Okay.
Excuse
So one
me, sir.
question.
Hello. Yeah. Yeah.
Sir,
Manoj, go ahead.
in a weighted majority game, what will be phi IV?
No, we have no idea, because we have to decide what phi is. Phi is like a solution concept, right? V is the game, right? V is like the game, right? And we have to define a solution concept.
Why
called a power index. Think of the power index as the
Okay,
solution concept, or the value operator, the
Okay,
analog of that.
Sir?
Huh. Yeah.
Actually, so is the set capital N fixed in this discussion?
Well, I will have examples where I may want to. Well, I mean, it's not critical. I mean, in one case, what we will do is that we will vary n, and we will compare the ratio of the powers of agents, who are present in both games and things like that, right? So I mean, mostly it will be fixed. Yeah, but I mean, nothing.
So
nothing
my question
hinges on
stems
that.
from this.
Yeah.
Yeah, but my question comes from this. Look at this second n. Should it be 0, 1 to the n or something?
Yeah, absolutely. So absolutely. Here is a major typo. So power index is a map from 0, 1 to the power of n. Absolutely. 0, 1 to the power of n. So I was going to write this for absolutely. 0, 1 to the power of n. So every player has a power, and the sum of these is equal to 1. Okay. The only difference between a power measure and a power index is that the sum of the powers don't have to add up to 1. Okay.
The Shapley value will be an index, right?
Absolutely. So that is what we're going to do now. So the Shapley value applied to voting games is called the Shapley-Shubik power index. Okay. And so here is here is since the voting game is more specialized than a general game, we can be a little more specific in our description of the power index, right? So the power of index, or the power of player I, whatever. So the Shapley-Shubik power index of V, which is denoted by SSV, is the Shapley value of the game V, right? And its ith component SSIV is the power index of player I. So how do we define it? So we again construct these orderings of the players, and we say that a player I is pivotal in an ordering if it is the case that the value of the players who precede I in the ordering, they have worth 0, but as soon as you add 1, as soon as you add I, the worth of that coalition becomes 1. In other words, the marginal contribution of player I to the coalition SIP is 1. Right? So the coalition of players preceding I in P is losing, but adding I to the coalition makes it winning. Okay. And what is the Shapley-Shubik power index for player I? All you do is that you count the number of preference, count the number of orderings such that I is pivotal in P, and you count them and you divide by n factorial, which is the total number of preference order. Although I keep saying preference order, the total number of orderings. Okay, so you see, this is exactly the Shapley value, because V for any coalition is either 0 or 1. So we look for players who make. We are interested only in players who make a positive marginal contribution, and that contribution can only be 1. You can only move the needle from 0 to 1. So if you do so in a particular ordering, then if you do so in a particular ordering, then you are pivotal. And then for a player, you simply count the number of orderings where I is pivotal and divide by n factorial. Okay, now you can also do the same counting via coalition. Okay, so what do we look at? We look at a player I, and then let us look at, let us do the following. We look at all subsets of n minus I with the property that S union I is winning and S is losing. So in other words, I is pivotal for the coalition S. It is pivotal for S. I'm going to use this term later. I is pivotal for S. I look at these things, but I don't just add up these coalitions. I don't add up I just don't count these coalitions. I do a weighted average of these coalitions, and the weighted average for is given by s factorial into n minus s minus 1 factorial divided by n factorial, divided by n factorial, right? Where small s is the cardinality of S. So instead of counting, pivotality across orderings, I now count pivotality across coalitions, and I do so. Then for certain coalitions it's 0, for certain coalitions it's 1, and then I take an average, but I don't take the uniform average. I take an average which depends on the size of the coalition. Now, recall what I was doing earlier. When I was talking about symmetry, I was doing something. It was clear that I was, looking at marginal contributions to coalitions, and then I was weighting them differently depending on the size of the coalition that you were contributing to. Okay. Now, this is important because we will contrast it with some other measures where you count differently. Okay, so now let's do something which you probably have done in your homework already. So consider the majority
Excuse me,
gain.
sir.
Yeah.
So just a small clarification here. Power index is a value, but power measure is not a value, right? In the
the sum. Yeah, so if I have a power, this thing which is a power index for player I, then if I add across the players, then I'll get 1. And if I have a power measure, I will not get 1
so
necessarily.
it's not a value.
It's not a value operator, if you wish. Yeah, that is. So it doesn't split the grand coalition. You by dividing by the sum of the power measures of players, you can get an index.
Yeah. Okay.
We'll come up. We'll look at a whole lot of examples. In due course.
Okay, sir.
Okay.
I also have a doubt.
Huh.
So when you said that this Shapley-Shubik power index is Shapley value of B, so here B will be the weighted majority gains, or Not very clear.
No. I mean, where? No. I mean, not the weighted majority game, but any voting game. A voting game is just a game where the values of coalitions lie between 0 and 1, and it has this monotonic structure. It's just a particular cooperative, it's a particular game in coalitional form. That's all. So the Shapley value is defined for all games, correct? Whatever the V of S, whatever that is, I can define what the Shapley value is. And what it does is that it adds if these are numbers for each player, and when you add them up, you'll get the value of the grand coalition.
Okay.
Yeah. And a voting game is just a subset of the class of coalitional games where the value of any coalition is either 0 or 1, and there is this monotonicity structure. That's all. So I can apply since I can apply the Shapley value to any game, I can certainly apply it to voting games. A majority game is a particular voting game, right?
Okay.
I can have voting games which are not majority games.
Okay.
Okay, so now consider the weighted majority game 1, 2, 3, where W is 1, 2, 3, Q is 4. Okay, so now let's quickly check this. 1 is pivotal only in the ordering 3, 1, 2. So 1 has weight 1, right? And you need 4. So 1 will be pivotal only if it comes second to 3. Because 3 will be contributing 3, and then 1 will add 1, and then you will hit the quota. So out of the 6, you will only, one, the Shapley-Shubik power index for player 1 is 1/6. Interestingly, it is also 1/6 for player 2, although he has a larger weight. Why? Because 2 is pivotal only, again, in the case when he's preceded by 3. Okay? There is no other situation where, if 3 is ahead of him, then he will be pivotal only if he comes second. If he comes third, then 1 will be pivotal, is enough, this thing. It's sufficient to make the coalition winning, and 1 and 2 by themselves are not winning, right? So 2 is pivotal only in 3, 2, 1. So also has Shapley-Shubik power index of 1/6, and all the others, 4 in the other 4 permutations, 3 is pivotal. Like in 1, 2, 3, 1 and 2 together contribute, have a weight 3, but that's not that's not enough to cross the threshold of 4. So 1, 2, 3, in 1, 2, 3, 3 is pivotal. In 1, 3, 2, 3 is pivotal. In 2, 1, 3, again 3 is pivotal, and in 2, 3, 1 also 3 is pivotal. Okay. So here is another, it's what you might call a real life example. It's a favorite of all these games. Is the United Nations Security Council. Okay. So, was there a question? So the Security Council was restructured in 1965. What was its structure pre-1965? There were 5 permanent members. The US, in those days, the USSR, Great Britain, France, and China, Taiwan. I mean, for a while, Taiwan took the place of China, and then it was only in the 70s that Taiwan was replaced by China. Okay, and I shall denote these permanent members by the set of permanent members by P. Now there are 6, in those days there was a Security Council, and there were 6 non-permanent members of the Security Council, and that I shall denote that set by NP. And so here were the rules of the Security Council. In order for a motion to pass, at least 7 votes were required. and all members of P had a veto. So we can write down the voting game as follows, that a coalition S is winning only if S contains all members of P and 2 out of the 6 non-permanent members. Okay, so if S was at least 7, if the size of S was 7, and P was a subset of S, then the coalition S was winning. Otherwise, you get 0.
Sir, would it be possible to define a value function if abstaining from voting was allowed?
You know, it's not, I mean, you'll have to say how you will change the value function. Correct? So in general, in this case, you would not. I'm not sure what that would mean. Yeah, I mean, this is really a binary world, actually, in which you agree or you disagree. And if the set of people who agree is a winning coalition, then you adopt. Right?
Okay.
I don't know if there are other ways. I mean, there is some people have tried to extend it, but really, you get the nicest results in this framework.
Okay, sir.
Okay. So let us calculate the Shapley. Let us calculate the power index for each player in this game. What am I doing? I'm going backwards. Okay. So notice that all members of P are substitutes of each other, and all members of NP are substitutes. So they will all receive the same thing. They're symmetric. Okay. So that part is clear. And now let's ask the question, let's pick an I in the set of non-permanent members, and let us ask, when is this member pivotal? Okay, what are the orderings for which I is pivotal? Notice what must be the case. It is pivotal if you remove that player, all the guys, all the players before I are non-pivotal. As soon as you add I, it becomes pivotal. What does it mean? It means that the 5 permanent members are ahead of I in that ordering. What is more is that there exists another non-permanent member who is also ahead of you. Okay, now you have 6 non-permanent members. How many ways can you choose the extra non-permanent member? 5 ways. Okay, you can choose the non-permanent member in 5 ways. Then what can you do? Then what you do is that you have 6 players ahead of you. You have to be in the 7th position. The 6 players ahead of you, you can shuffle in any way you want. So that's 6 factorial. After you've come, you're the 7th player. There are 4 players behind you, and you can shuffle those players in any way you want. Right? Divided by the total number of players, that's 11 factorial. Is that clear? Do you understand this calculation? The index for a non-permanent member, do you understand this?
So, but why did we multiply it by 5 over here?
Because you can choose the extra member of the non-permanent members who also come ahead of you. Okay. So suppose there are 6 non-permanent members. 1, 2. Suppose the permanent members are A, B, C, D, E, and there are non-permanent members 1, 2, 3, 4, 5, 6. Okay. So you are, let's say, 1. Now you are counting orderings. So there are 6 guys ahead of you, which include all the permanent guys. That's 5. But you can choose the 6th guy who is a non-permanent member from 2, 3, 4, 5, 6. So that's 5. Yeah, you can choose one of them. So for instance, I can have A, B, C, D, E, and 3. These are the guys who are ahead of me. And how many ways are there? How many ways are are there to do it? I obviously can shuffle these guys in 6 different ways. There are 6 guys, they can enter in any way. Correct? And similarly, the guys after me, who must all be non-permanent members, there are four of these guys, they can come in any way. Right? So that's 4 factorial. Is that clear? The 5 is because
Yes, sir.
the 5 is because you can choose the extra non-permanent member in 5 ways. Okay, so if you do this, computation, then you can see that the Shapley value of a non-permanent member is 1 over 462, which is 0.00216. So what is the total power of NP members? It's 6 over 462. And that works out to 0.013. And the total power of P is 456 over 462. It is the residual 1 minus this, because it's a power index. It adds up to 1. So it's 456 over 462, which is 0.987. And if you think about it, the power of the permanent members is 98%. And of the non-permanent members, it is 1.3%, essentially. Okay? And the power of a P member is 456 divided by 5 into 462, because there are 5 permanent members. And if you look at the ratio of the power of a non-permanent member to a permanent member, it works out to 1:91.2. Okay, according to the Shapley-Shubik power index. Is that clear? Is that are there any questions? Right. So I'm just counting. Right. You have these orderings. So there are 11 players here. There are 11 factorial orderings of all these players. Okay. So I say player I, who is, let us say, player 1 amongst the non-permanent guys, and I look at all the notice one other observation. In any P, there is exactly one player who is pivotal in that ordering. So there is exactly one, because when you at null, which you start from null, it's 0, and at n it is 1. Okay, as you go all the way, you look at the power of the coalition of the guys from the top to that point, right? So it's all 0. Then at some point it has to become 1, and once it becomes 1, the marginal contribution cannot exceed, must be 0 again. Right? As soon as you flip from 0 to 1, that guy has a marginal contribution of 1, and then thereafter it's all 0 again. So in every P, there is exactly one player who is pivotal. And for player I, you just keep searching for the P's where I is pivotal. You tick them off, and then you add them up. You just add them. You add up all your ticks, and you divide by 11 factorial, and that is the Shapley-Shubik index of that player. Okay? And okay, this is 91.2.
So when you've taken the ratio, of one member of non-pivotal to one member of pivotal.
Yeah, exactly. Right, as an index of, one guy is 91.2 times more powerful than the other. Okay, so now it was felt that the power structure in the Security Council was very unbalanced. This was something that grew out of the exigencies of World War II. So where the permanent members were essentially the guys who won the war. So they said there were other countries who started saying that, look, I mean, we deserve better representation. So the permanent members, of course, didn't want to give up their veto, which would be the way to make it fair. But they played a trick. They said, okay, what we will do is that we will not increase or decrease the number of permanent members. What we'll do is that we'll add more non-permanent members and we'll increase the quota. Okay, so this was the post 1965 structure. What you did was you had the same 5 permanent members as before, and they retained their veto power. But you added 4 more non-permanent members, so you had 10 non-permanent members. And the other thing is that you now increase the quota to 9. So for a motion to pass, 9 votes were required. So in other than the 5, you needed 4 more non-permanent members, right? And they said, okay, we've added more non-permanent members and we have a higher approval quota, so we have more power to the non-permanent members. So what we can do is that we can do a quick check of the Shapley-Shubik power index and see if that bears out the claim that, and to see what the new distribution of power is. Okay. Any questions? So again, we calculate the Shapley-Shubik index for this new voting game. And again, I ask, what are the orderings P for which I is pivotal? So notice that now SIP, which is the set of players which precede I in P, there must be 8 members, okay? Because the coalition is, because the quota is 9. Now, what must SIP be? It must contain all members of P and 3 members of NP, because that will make up 8. 3 members of NP other than I. Yeah, other than I. Okay. So now, what is the Shapley-Shubik power index of I? What you can do is that now, instead of the 5 that we were doing before, we have to add 3 more players from the 9 remaining non-permanent members, right? So that's 9 choose 3. Okay. And now once you have this 3 members, how many orderings are there which keep this player I at the whicheth place? At the 9th place, and have keep this player I at the 9th place, have all the 5 guys of the permanent of the P set above, and all the extra 3 chosen guys of the NP set also above, and the remainder below. So what is it? So there are 8 guys above you. So it's 8 factorial into, and who are the guys below you? There are 6 guys below you. You can shuffle them around in any way you want, and you divide by 15 factorial. Okay, so it's exactly the same calculation as earlier. Earlier you were using 5 choose 1. Here it's 9 choose 3. Yeah, and essentially the set of players ahead of you is 8 factorial. The set of players behind you is 6 factorial, because you are in the 9th position. Okay, so if you do this thing, apparently it turns out that the number is 4/2145, and which is 0.00186. And the total power of NP members is 40/2145, which is 0.0186. And the total power of P is 0.9814. Okay, so and the power of a P member, permanent member, is now 0.1963. So how has it changed? Earlier it was, where was it? 0.987, and from 0.987 it is now 0.981. So there is a change, there is a reduction in the 3rd decimal place. But interestingly, now the ratio of power of NP to P actually increases, because now there are more P and NP players. There are now 10 NP players. Okay, so if you look at the structure, if you look at the ratio of power of an NP to P, it actually becomes even worse. Yeah, it used to be 1:91 point something. Now it is 1:105.25. So actually the relative power of the permanent members has increased even more. Okay. So here's an illustration. So is that clear? Is any questions? Okay, now what we're going to do is that we are going to discuss some other power indices, right? And in fact, there is a whole plethora of such indices. I'm sure that after this lecture, you guys should be able to propose a few yourself.
So one question quickly. So in the previous format of the Security Council that you just discussed,
yeah.
So there were 5 permanent and 6 non-permanent members with the requirement of 7 non-permanent, right?
Yeah. Yeah.
And you needed a what? Minimum of 6.
You needed a minimum. No, you needed
minimum of how many? What was the format? The one previous to this.
Of 2 non-permanent members to join in along with
the
5
quota was
permanent.
7. There were 6 non-permanent. There were 6 non-permanent members.
Right. So the quota was 7, right?
Wow. The quota was 7. The quota was 7. Yeah.
Yeah. If you kept the quota same and reduced or increased the number of the permanent members, either reduced or increased, whatever you wish.
So reduce would surely reduce their power. No, reduce would increase their power. I don't know actually. So I mean,
Is it obvious?
It's not obvious actually. You'd have to do the calculations.
I'm keeping the quota fixed, right?
I'm keeping the quota fixed. My guess is that the power of every single member might increase, but the aggregate power might decrease of the members of P.
So is there like a situation where there is a maximum and either way things go down, either in terms of the total power or individual power of the permanent members?
You see, there are questions of monotonicity and so on. You can phrase axioms regarding monotonicity and so on. I mean,
no. But my question is just using the Shapley-Shubik index. I mean, what is the optimal number of permanent members, which somehow makes them better off?
Which makes
given a quota.
No, I mean, for instance, if there is a single guy and he has a veto, then he gets Shapley-Shubik 1, right?
Yeah.
So that will make
him. He won't be allowed to do that.
Yeah.
Okay.
Yeah.
Thank you.
Okay. So this was an illustration of Shapley-Shubik. Let us now look at another measure and index called the Banzhaf index. Right? Sorry?
I have a question. So in those basis games, symmetry and dummy pin down the value exactly. Does that carry on to this class, which is a larger set?
No. You need a different axiom. Okay. So I'll maybe spend a few minutes at the end discussing some of those things, but not really. I don't really know it very well, and it's hard for me to get hold of those papers now. But you need a different axiom.
Okay.
You need a different axiom, right? So so I mean, you can create a new game from 2 games by taking the max and the min, right? Yeah. For every coalition. And as far as I recall, you need, instead of the additivity, straightforward additivity axioms, you need an axiom based on this. Anyway, we will discuss that. Okay. Let V be a be a voting game. Let I be a player and let S be a subset of N minus I. We now just define pivotality for a coalition S which does not contain I, right? Earlier we were looking at pivotality with respect to orderings. Now we are going to look at pivotality with respect to coalitions, right? And we could have done that in Shapley-Shubik as well, right? And taken an average over pivotality over coalitions, but then when we computed the index, we took a weighted average. Here we are going to take the uniform average. Now this is essentially the Banzhaf measure. So let capital MIV be the set of coalitions for whom I is pivotal, and let MIV be the cardinality of this set.
I didn't get how the notion of pivotal is different here. Up until now, we were considering orderings, right?
Yeah. So here I'm considering coalitions.
Okay.
So by the way, in Shapley-Shubik also we were looking at coalitions essentially, right? But the coalitions were specified by the ordering. And when I added them, I added them across uniformly across orderings. If I am adding them across coalitions, then I'm not adding uniformly. I am adding, doing a weighted average. Okay, here I'm going to change those weights. Just hang on for a minute. So small MIV is the cardinality of capital MIV. So it is the number of coalitions for which I is pivotal. So these coalitions obviously don't contain I. So a normalized Banzhaf measure of I at V is MIV divided by 2 to the n minus 1, which is the total number of non-trivial coalitions. I don't know whether it should be, there is a convention of sometimes not including the null coalition.
So it should be -1 should not be in the power, right?
Yeah, absolutely. Absolutely. I'm sure I've made this, so I should correct this. Yeah. So the total number of oh, hang on. No. So these are the set of, it should be in the power because it's the power set of all, it is the power set of all voters.
Not containing I, right?
Not containing I. So it is 2 to the power n minus 1. Okay.
Can you repeat how is it -1?
So what are the set of all coalitions to consider when you're considering the pivotality of I? They are all coalitions of players not containing I.
Yeah.
So 2 to the power n minus 1. So it's absolutely fine.
So here you have counted 5.
No. Yeah, here I've counted 5, and it's consistent with our first definition. Notice in our first definition, I said B of 5 was 0. I counted it, right? I mean, I'm looking at all sets. I'm looking at all subsets, including the null set. Otherwise, here it would be 2 to the n minus 1 minus 1, whatever. I don't think that these are, big deals, but the 2 to the power n minus 1 here is important. Right, because it consists of all subsets of players other than I. Okay, and now I can get the Banzhaf power index for I, which is just MIV divided by MJV, and I sum over J. Okay, so what is it? Yeah, the 2 to the n minus 1 is irrelevant here. They'll cancel. So what is it that I'm doing here? I am counting the coalitions. For every player, I'm counting the coalitions of players not including I for which I is pivotal, right? I list them all. I put a tick whenever something is pivotal, and then I count the ticks, right? And then I do this for every player, and then I just take the average.
So this
I mean, I
PAR
take
index,
the ratio, yeah.
so the PAR index where the denominator has summation over NJV.
Yeah. So that's why I've made it
Can you
power index, so
explain
that
the
it's
integration?
yeah. So it'll make the sum 1.
Okay, yeah.
Yeah. Whereas the Banzhaf measure is not.
Yes,
The
sir.
Banzhaf measure is not. Okay. Okay. So so what is the difference between Banzhaf and Shapley-Shubik? It is you know, I think it will be made clear by the next example. Or let me say this again. So there, you know, you can think of the Shapley-Shubik as again, for every player you list the coalitions which are for which you are pivotal, and then what you do is that you take a weighted average of these things, where the weights depend on the size of the coalition to which you are added. Okay, and in the Banzhaf you don't do that, you simply add them. Okay, so let's take this example. This is the earlier example. So n is equal to 1, 2, 3, a typo here. W is equal to 1, 2, 3, and Q is equal to 4. Okay, we've seen that that the Shapley-Shubik power index is 1/6, 1/6, and 2/3. Okay, because there is exactly 1 out of the 6 permutations where 1 is pivotal. That's the permutation 3, 1, 2. 1 where 2 is pivotal, which is 3, 2, 1, and the remainder 3 is pivotal. Now let's compute the Banzhaf index, yeah, the Banzhaf. Let's just count the coalitions for each of the players over which they are pivotal, right? So for player one is pivotal only with respect to the coalition 3. What does it mean? 3 by itself is not, is not winning. You add 1 to it. 3 and 1 is winning. Therefore, 1 is pivotal to the coalition 3. Similarly for 2, and for 3, it is the 3 coalitions 1, 1, 2, and 1, 2. And so, what is the Banzhaf power index? Well, what is small m1v? It is 1. What is small m2v? It is 1. And what is small m3v? It is 3. So it is 1 by 5, 1 by 5, and 3 by 5. Okay, there is exactly 1 coalition for which 1 is pivotal, 1 coalition over which 2 is pivotal, and 3 coalitions over which 3 is pivotal. Okay, so you take the uniform average over pivotal coalitions, over coalitions for which you are pivotal, I should add. I should be clear, right? And the Shapley-Shubik, you can do Shapley-Shubik in the same way, but you will give different weights to different coalitions depending on the size of that coalition. So SS does not count all coalitions equally. For player 1, the singleton coalitions 2 and 3 are given weight 1/6. Correct? And the coalition 0 and a null and 2/3 have weight 1/3. Now, why is that? Why does 2 get weight 1/6? Because there is exactly 1 permutation in which 1 adds is pivotal with respect to the coalition of players which preceded, which is 2, 1, 3. That's only 1 out of 6. And for 3, it is exactly 1 out of 6 as well, because it's 3, 3, 1, 2. But for the null, there are 2 permutations. It is, for null, it is 1, 2, 3 and 1, 3, 2. Right? There are 2 permutations where 1 appears first. And similarly, there are two permutations where one is being added to coalition 2-3, which is 2-3-1 and 3-2-1. Therefore, these coalitions have higher weight. Okay, so again, what you're doing is you're aggregating pivotality, you're counting these ticks, which is when pivotality occurs, but you're taking averages over coalitions in a different way, depending on the size of the coalition. For Shapley-Shubik, the size of the coalition matters for over which you're pivotal. In Banzhaf, it does not matter. Is that clear? Okay. So these are kind of like the two important measures. I mean, two important measures in the sense that, I guess there are most papers written about it. Okay, let's just not push it beyond that. Now, I'll now propose a whole bunch of other measures, and you'll see that each one of them has a point. One is the set of things which are actually related to the Banzhaf thing, and these are called Coleman measures. And a little bit of notation. So let WV be the set of winning coalitions of the game V. So S belongs to WV, V of S is equal to 1, and LV is a set of losing coalitions. Whatever, this is equal to, V of S is equal to 0. So what is, we are going to define measures now, not indices. So this is called the Coleman preventive measure for player I in V, which is simply small m1v over the cardinality of winning coalitions. So what is it supposed, what is the interpretation here? So, so suppose S belongs to capital MIV. So small MIV is just the number of elements in capital MIV. Then S union I is a winning coalition that I can prevent from winning by withdrawing her support. Okay, so what are the winning coalitions where I is crucial or critical or whatever? So Coleman proposed two measures of power. One is the power that a player has in destroying a winning coalition, and the second one in creating a winning coalition. Okay, so in this case, in the preventive measure, you simply look at the you look at all coalitions which are winning when you are there but are not winning when you're removed, and that's exactly MIV, because S is losing, S union I is winning, right? So MIV is exactly the number of coalitions for which you are critical, in that sense that removal of support leads to this coalition not being winning. And what is the measure? It is the fraction of winning coalitions that are vulnerable to I, where these coalitions are winning, all these coalitions are winning, but in the numerator we are counting only those coalitions. We are counting those coalitions where the withdrawal of I's support means that the coalition collapses. It's no longer winning.
So the index that this will create will be the same as the previous one, right?
Yeah. The index will be the same, but the measure is different. Okay, and there are some results actually. Yeah. So the other thing is the Coleman initiative measure, which is it's the same MIV but divided by the set of losing coalitions. So what does it mean? So here, let us see, S is a losing coalition, but I can make it a winning coalition by joining it, by adding her support. Okay, so CIV is kind of a measure which says that I is, if this measure is high, I is powerful because it can basically transform losing coalitions into winning coalitions. It can add that extra zing to these coalitions. Okay, and the preventive one says that if you remove those things, if you remove that I, then then they will then the coalition is losing. So you can see that there are two different measures of power, as it were, depending on how what you divide by. And then
so
you can
these are
write.
measures,
Sorry.
and these are measures because small MIV is less than equal to min of.
No, because they don't add up to 1. If you make them add up to 1, they'll be the Banzaf.
No, but they also are required to be less than 1, and they are less than 1 because of MIV being smaller than
Yeah. It's a subset. Yeah, capital MIV is a subset of this thing. Yeah, so they'll be less than 1. Okay, it's a fraction of losing coalitions, etc.
Yeah.
Okay, and then you can write this thing about the relationship with the Banzaf, the Banzaf measure, and these two things.
As the harmonic mean, is it?
Harmonic mean, exactly. It's the harmonic mean of these two things, right? But this is again a popular thing. You can work these things out, and a player's power. Another, one way in which you can think of these things is that they measure different aspects of the power of a voter.
So
Okay.
I don't see how this last equation holds.
No, it's not. No. I mean, it comes from the fact that the set of winning coalitions plus the set of losing coalitions is equal to 2 to the power n.
Yeah, but mathematically, if we try to calculate,
I don't think it's hard. I mean, remember LV plus WV plus LV is equal to 2 to the power n, which I wrote earlier, and I think some manipulation will give you these things.
No, it's right here. So 2 to the power n divided by 2 is 2 to the power n minus 1. You are done.
Yeah. So it's just some simple manipulation. I didn't check it, but it has to be that. There's nothing. Okay. So here's another index called the Deegan-Packel index.
So I have a small doubt. So in the previous slide, how is CIV, when we take the losing coalitions in the denominator, how is that less than 1?
How is that? What is less than 1?
The measure.
Yeah, because the measure is because MIV is the MIV is the set of MIV counts the number of losing coalitions which become winning if you add I to it. So that must be a subset of the set of all losing coalitions.
Okay.
Yeah. So all the S's are losing. Then you add I to it, they become winning. You count the number of such S's, that's MIV. That is clearly a subset of the set of LV.
Sir, but CPIV may not be less than 1, right? Because
but it's the same thing. MIV is also the set of, it's also the set of coalitions where if I remove I become losing. Yeah, S becomes losing. So
yeah, but then MIV may be a larger set than WV.
No, WV is a set of all winning coalitions. S union I is a set of winning coalitions.
Both of these are ideally less than equal to 1 only, right? Because the set of all includes this.
Yeah. But it's just the set of winning coalitions. Yeah, I mean it's the proportion of winning coalitions where I is critical, and there's a set of losing coalitions where I is very valuable. So those are the two these things. Okay, so here, for instance, I'll describe two other indices. One is this Deegan-Packel index, which is, we were discussing this thing of minimal winning coalitions. So what's a minimal winning coalition? If it's a winning coalition, but no subset of it is winning. Right, so take any player out and it's no longer winning. Okay, and MWV and MWMVIV denote the set of minimal winning coalitions and the set of minimal winning coalitions containing I respectively. Okay, so a coalition is winning if if it gets one and remove anybody from it and it starts getting zero. And MVI is the set of minimal winning coalitions where I is where I is a member of that winning coalition, right? So for instance, so if I have a majority game, what will be the set of minimal winning coalitions? So suppose there are 3 players, okay, 1, 2, 3, and I'm looking at a majority game. Suppose I look at player I, what is the set of minimal winning coalitions for I? They will be the sets 1, 2, and 1, 3. Yeah. And because if you remove any one of them, then they will no longer be winning. And one belongs to both these winning coalitions. And what is the set MV? It is the set 1, 2, 1, 3, and 2, 3. They are the minimal winning coalitions. So
and
what does
these capital MWs are non-empty, right? Because of the grand coalition.
By the
grand coalition is present in
yeah. The grand coalition.
Sorry. Not the grand coalition. It may not be minimal, right?
The grand coalition may not be minimal, but as
because V of n is 1, both of these are non-empty.
Yeah. So as I and when I remove everybody, it's going to be 0. Then it will no longer be winning.
Why would you remove everybody?
No, to show that there are some minimal winning coalitions.
No, that is fine, but I'm saying that MV subscript I of V is.
It may not be. Yeah, no. It may be 0. It may be 0. I mean, it may be a null set.
The second one, but the first one has to be.
Yeah. Okay. So, for instance, look at the dictator game, right? So, and look at a player who is not the dictator.
Yeah.
So, there for any player who is not the dictator, the set of minimal winning coalitions with the dictator is going to be
empty because he requires I as well. Right?
He requires I.
Yeah, which is not, and dualtons are not minimal.
Yeah, exactly. Okay. So I pare it down to the smallest winning coalition, and if it contains I, then that's a minimal winning coalition containing I.
Right.
So, but how is it null in case of dictatorship?
No, other than the dictator. Suppose player 1 is the dictator. I claim that there is no minimal winning coalition with player 2, say.
Shouldn't 1, 2 be the winning coalition?
Yeah, but it's not minimal. Because if I remove 2, then 1 is still winning.
Okay.
Yeah? A minimal winning coalition has the property that if you remove any player from it, then it will no longer be winning. No subset of a minimal winning coalition is winning.
Got it.
Okay, so Deegan and Packel took the view that a player derives power only by being a member of a minimal winning coalition. And moreover, in a minimal winning coalition, all players share power equally. Okay, so what you have to do is that you have to write down all the minimal winning coalitions for each player. Okay, and basically DPIV is the sum. So how do I compute the index for player I? I wrote MS. I'm sorry. By the way, I apologize. I should have made it MW everywhere, and one place I've used MW, in another place I've used MV, and in a third place I've used MS. So I will make these changes. It will be MW everywhere. Okay. Okay. Do you see in the second bullet point I've written MW and then MV? They should be both minimal winning W, and then in the last slide it should be MWI. Okay, so this is the Deegan-Packel index, right? So
I don't see why point 2 and the formula agree. I mean, could you explain that?
Point 2 and the formula?
Point 2 is saying that all power in a minimal winning coalition
Point
is
3.
shared. What is 3?
Yeah. So look at player I. We are looking at the index for player I. Okay. So what you do is that you look at all minimal winning coalitions involving player I. That's what I'm summing over. Okay. And for each of these coalitions, so there is coalition 1, there is coalition, S1, S2, S3, S4, right?
Right.
What is the power that I get? From each one of them, I get 1 over the cardinality of that set. And I add them up.
Oh, okay. Okay, fine.
Okay. So do you see what do you see what we are doing here? What we are doing here is the following. We fix a player I. Okay, we fix a player I, and then we look at all coalitions where this player is where we look for all coalitions where the coalition is a minimal winning coalition and I is a member of that coalition. Okay, now what we do is that for each of those coalitions we give a weight to player I, and what is that weight? It is 1 over the cardinality of that minimal winning coalition. Okay, and then we add it across all these things, and then we normalize it.
Sir, and this is an index because
it should add up to 1. Huh? When I interchange and I do it, it should add up to 1. I'd convinced myself earlier, but I'm sure it does.
Okay, it's because that we are counting each winning coalition.
Each winning coalition, the aggregate weight for any winning coalition, the aggregate weight for any winning coalition is 1, because it's 1 over S, where S is the size, right? So when I add it over all the players for each winning coalition, I will get each minimal winning coalition. I will get 1.
Yeah.
Right. So I keep adding them, then I will get the total number of minimal winning coalitions.
Yeah.
Right. And I'll get 1. That's why it's an index.
Yeah.
Okay. So this seems like a reasonable point of view to take as well, right? I mean, your power is your power only in critical coalitions, which you can think of as minimal winning coalition.
So, sir, as you can see, like some of these indices, like for dictatorships, they might give the same power.
They have to. If you construct an index which doesn't give all power to a dictator, people are not going to like your index.
So do we have like defined axioms or some things which these indices must satisfy?
If it satisfies dummy, then it has to, right?
Sorry?
If it has to, if the index satisfies dummy,
yeah,
then it will always give full power to the dictator. Is that correct?
Yeah. I think so. Anything which satisfies dummy will have that power. Have that this thing. But are you asking for characterizations? I'll say a little bit more about characterizations. I'll go on for another 5 minutes and then. Yeah.
Sir, in a dictator game, suppose I is a dictator and J, and we look at the coalition IJ, then the set J does not have any value, but IJ does.
Yeah.
So,
but it's not a minimal winning coalition.
Right.
It's not a minimal winning coalition.
Right.
Okay. So here is the last index, the Johnston index. So here is a criticism of the Banzhaf index. A player is assigned a score of 1 for every coalition for which he's pivotal, right? What we did was for I, we enumerated all the coalitions not including I, and then we ticked off those in which he was pivotal, right? And then we added the ticks essentially, right? And divided by the right thing. But the criticism is that you did so irrespective of how many other voters were pivotal in that coalition. Okay, this is kind of like related to this Deegan-Packel, this thing, right? So, for instance, look at suppose coalitions of size 2 are minimal winning coalitions. Now, if you look at 1, 2, 3, then in some sense, what was I forgot what I was trying to say. Many players can be pivotal in a coalition, right? I mean, it's not that one player is pivotal, right? Each player can be pivotal, right? So, for instance, you need 3 players, to get 1, and 2 will give you 0. Then every player is pivotal in a 3-player coalition. Okay. Now, what the Johnston index does is that it divides what it does is that it does not count it as one. It just counts the number of pivotal players for a coalition. So once again, like the Banzhaf index, I write down all I write down all the coalitions, not including I, and then instead of a tick, together with the tick, I give it a weight. And what is the weight? It is 1 divided by the number of players who are pivotal in that coalition. Okay, and then I create this Johnston index, and then I again normalize, and I get that, right? So think about it. It's just a variant of the Banzhaf index. So all these things are essentially variants on the same theme.
So it's the same for each individual here. Like the notation wise, it's JV. So it should be for each individual, right?
Yeah, it is JIV here. It should be. Yeah, I'm sorry, I missed. I'll make a note of these things. JIV.
And that is how it will sum up to 1 again.
Exactly. That's how it will sum up to 1. But how do I calculate JIV? I look at all these coalitions S, not including I. Then for each one of them, I see the number of, I see the players who are pivotal in them. And then I make this adjustment, right? 1 over pi, 1 over the number of players who are pivotal. Okay.
So one question.
Yeah.
So here you were saying that for any arbitrary coalition S, we are looking at the number of pivotal players, right?
Yeah. So I should say for any coalition S, pi V is the set of players who are pivotal at S. Yeah.
And suppose you actually added the qualifier that for only minimal coalitions you were doing this.
Yeah.
Then you would have gotten back to the previous slide essentially, right?
Yes, then I would have gotten back because I do 1 over that. Yes.
Yeah. Okay. Thank you.
Yeah. Okay. So again, the basic point is that the power of a player in these voting games clearly depends on the pivotality of the player. If he can change some coalition from 0 to 1. But there are many players who are changing this over many coalitions. So the point is, how do we ascribe power to each player? And there are many ways of doing this, as you can see, right? The Shapley-Shubik is one, using orderings. Banzhaf takes the average over all coalitions, and those other indices are all variants, minimal winning coalitions, etc., etc., etc. So I'm sure you can think of others as well. Find mixtures of all of them. Anyway, so let me just conclude by a few remarks about characterization. The characterization of the SS power index does not follow from Shapley's axiom, basically because as I was saying earlier, the additivity axiom does not apply to voting games. Okay, it does not apply to voting games because, Vn plus Wn is 2, for instance. So we require different axioms. And Pradeep Dubey in his 75 paper, did characterize the SS index. And by using a variant of additivity, I don't recall the details, as I said, but essentially you can create games by looking, take games V and W, and for every coalition, you take the max of V of S and W of S, and in other case, you take the min. So in one case, if both are 1, then you get 1. Both are 0, you get 0. In one case, if one is 1 and the other one is 0, for the max you take 1, for the min you take 0, right? And basically, the variant of the additivity axiom that you use is that something like V of the phi of V plus phi of W is the phi of the max game plus the phi of the min game, or something like that. So you have some variant of additivity which works. And then, Dubey and Shapley in 79 also characterized the Banzhaf index. That's a well-known paper. Yeah. But I mean, the characterization of these things is it doesn't follow immediately from axioms on all games, because of this sort of restricted domain feature of voting games. Okay. Any questions? I will try and eliminate the typos here and send it to you again. Did you guys get to see the video of the last lecture? Hello?
Yes, sir.
Okay. Fine. So any questions? Shall we stop?
So are we having class next week at the same, according to the same schedule?
Yeah, why not?
Okay.
Yeah, I will send this thing out in the afternoon at some point. Okay?
Okay, sir.
Okay. Bye.
Thank you, sir.
Thanks.
Bye, sir.
Thank you,
Take care.
sir.
Bye.
Now what? Leaving meeting. Yeah, leaving meeting.